Till now we have seen about the transformation of position coordinates. Now let us see what happens to the distance or length during the Galilean transformation. Let us say that in the S and S dash frame, where S dash is in relative motion with a velocity of v with respect to S, the particle is changing its position from P1 to P2. Let us say that the coordinates of the position P1 in S frame are x1, y, z, time t1, and the coordinates of position P2 in the S frame is x2, y, z, and t2. Similarly, when we make the measurements from S dash frame, P1 is x1 dash, y, z, t, and P2 is x2 dash, y, z, t. Okay. So sorry, this is t1 dash, this is t2 dash. From the Galilean transformation equations, we have x1 dash equal to x1 minus vt, where v is the velocity, the relative velocity of s dash with respect to s. Since there is no motion along y-axis and z-axis, therefore we can write y dash equal to y, z dash equal to z, t1 dash equal to t1. Similarly, x2 dash is equal to x2 minus vt, v to t, y dash equal to y, z dash equal to z, t2 dash equal to t2. So what we are measuring here is transformation of distance or length. The distance traveled by the particle from P1 to P2, it is given by delta x in S frame and delta x dash in S dash frame. Since there is no motion along y-axis and z-axis, therefore the displacement or the distance traveled by the object along y-axis and z-axis is 0. Let us find out what is the distance traveled by the object along x-axis. Delta x dash is equal to final position in S dash frame x2 dash minus initial position of the object in the S dash frame, that is x2 dash minus x1 dash. Delta x dash is equal to x2 dash is x2 minus v into t, x2 minus v into t, minus x1 dash is x1 minus vt, where we assume that t2 dash minus t1 dash is also equal to t2 minus t1 in the S frame. This is equal to t. Therefore, we can write delta x dash is equal to x2 minus x1 minus vt, minus of minus plus, since negative is outside the bracket, therefore minus v into t. Delta x dash is equal to x2 minus x1 minus vt minus vt, 0. Delta x dash is equal to x2 minus x1 is change in position in the S frame, therefore we can write it as delta x. From this expression, it is clear that the distance traveled by the object as measured in the frame S dash is equal to the distance traveled by the object as measured in the S frame. Therefore, the distance is invariant under Galilean transformation. Till now, we have seen about the variation of distance or length with the Galilean transformation. Now let us see what happens to the velocity because of Galilean transformation. Again the same considerations. The object is moving from P1 to P2. At P1 the same coordinates. From Galilean transformation we have x1 dash is equal to x1 minus t1, where the time is t1 dash when the object is at point P1 in the frame of reference S dash, and similarly x2 dash is equal to x2 minus t2 dash, where t2 dash is the time in the S dash frame when the object is at P2. From the definition of velocity, we know that velocity is equal to change in position, that is displacement, divided by change in time, Let us say that u dash is the velocity of the object in the x dash frame of reference. Therefore, we can write delta x dash divided by delta t dash. Change in position of the object as measured from the s dash frame. Delta t dash is the change in time as measured in the s dash frame. U dash is equal to delta x dash can be written as x2 dash minus x1 dash divided by t2 dash minus t1 dash. U dash is equal to x2 dash is, what is x2 dash? x2 dash is x2 minus v t2 dash. x2 minus v t2 dash minus, what is x1 dash? x1 dash is x1 minus v t1 dash divided by x2 dash minus t1 dash. U dash is equal to x2 minus x1 minus, here v, we can take minus v common. What remains here? t2 dash, minus into minus plus, minus is outside, therefore minus t1 dash divided by t2 dash minus t1 dash. U dash is equal to x2 minus x1 divided by t2 dash minus t1 dash minus v into t2 dash minus t1 dash divided by t2 dash minus t1 dash, where we separated the denominator for both the values. U dash is equal to x2 minus x1, it is nothing but displacement of the particle as measured from the s frame, because x2 is the coordinate of x and x1 is coordinate of x for the position p1. t2 dash, it is equals to t2, and t1 dash, it is equals to t1. Therefore, we can write t2 minus t1 minus t2 dash minus t1 dash divided by t2 dash minus t1 dash cancels. This is v. U dash is equal to delta x divided by t2 minus t1. It is nothing but change in time as measured in the s frame minus v. U dash is equal to u, velocity of the particle as measured in the s frame, minus v. So here you can see that the velocity of the object, velocity of the same particle is u dash in the s frame, s dash frame, and it is u in the s frame. Therefore, the velocity in the Galilean transformation varies. What about, let us say that a is the acceleration of the particle in the s frame, which is equals to du divided by dt, and a dash is the acceleration of the particle in the s dash frame, which is equal to du dash divided by dt. From the transformation of velocity in the Galilean transformation, we got the equation u dash is equal to u minus v, where u dash is the velocity of the particle as measured from the s dash frame, u is the velocity of the particle as measured in the s frame. Differentiating this equation with respect to time, we will get du dash divided by dt equal to du divided by dt minus 0, because v is constant. Differentiation of any constant is 0. Du dash divided by dt, it is nothing but a dash. Du divided by dt, it is nothing but a. Therefore, we can say that the acceleration is invariant under Galilean transformation. Okay, so what to remember? The position is variant in the Galilean transformation. Second point, the distance or the length is invariant in the Galilean transformation. Third point, the velocity is variant in the Galilean transformation. Fourth point, the acceleration is invariant in the Galilean transformation.